Besides a standard format for a function equation where it just says f of x equals 2x plus 5 or something ordinary like that, we can sometimes have a function defined piecewise, or just call it a piecewise function, where what our equation is depends on what the input is. And so then we have to be given a set of rules to follow to determine what equation we plug our inputs into depending on what those inputs are. And so that's what we see here. And so we can almost kind of read this backwards, where our function g of x, as long as we're plugging in a number that is less than or equal to -2, has an output of 3. On the other hand, if our input is larger than -2, not equal to, because that falls into the previous category, but if it's larger than -2, but less than or equal to +2, then we're supposed to use this equation, x squared plus 3. And then finally, if our input into our function is greater than 2, then we're supposed to use this equation here 4 times whatever that input is. So this is what we mean by a piecewise function. So we have multiple different equations that we're supposed to make use of depending on the input. So if we take a look at this first one, we're asked to find g of 8, meaning that 8 is our input. So that puts us into that bottom category where x is greater than 2, our input is greater than 2. So that means I'm going to do 4 times 8. I'm going to use that bottom function. And so 4 times 8, my output is 32. If I go to the next example and I plug in 2 as my input, so now I see that that falls into the middle category. Remember, it's less than or equal to 2, so it's not in the bottom category, it's in the middle. So that means I'm supposed to use x squared plus 2 as my equation. So I'm going to do 2 squared plus 2. And so 2 squared is 4, 4 plus 2 is 6. For g of -6, so with an input of -6, that falls into that top category. -6 is less than or equal to -2. And so in that case, my output is just 3. No matter what my input is, as long as it's less than or equal to -2, my output is 3. Jumping to the bottom row, g of 0, so that falls into the middle category. So we've got 0 squared plus 2, so our output is just 2. G of -2, again, that's one of those border points, but it falls into the upper category since x is less than or equal to -2 is that first restriction. So that means our output is just going to be 3. And then finally, for g of 5, 5 falls into that bottom category. 5 is greater than 2, so we're going to use 4x, so 4 times 5 is going to be the function that we use, the equation that we use for this one, so we get 20. The other topic I want to discuss here is the idea of domain. We touched on this a little bit in previous work that we've done, but we haven't had a formalized rule or set of guidelines that we could follow. We just kind of looked at equations and functions on a case-by-case basis to determine what the domain is. So of course, remember, domain is the question of what numbers are you allowed to plug into a function, what x values, what inputs are contained in a graph. And so when we look at it from an equation perspective, our default position is that the domain is going to be all real numbers. So that's kind of our starting point. If we think of like a linear function or even a polynomial function, so something like f of x equals 2x plus 5, or g of x equals -x squared minus 3, or something along those lines. There's no restrictions, there's no limits on what we could plug into that type of function and into most functions as an input. We can plug in negatives, positives, 0, fractions, decimals, rational, irrational numbers, doesn't matter. We can plug in anything we want. So again, our default position is all real numbers. There are 3 primary exceptions to that, however. First is for rational functions. We've looked at these a little bit before. So for rational functions, the thing that we have to pay attention to is the idea that we can't divide by 0. So what we have to do in that case is we have to check to see, are there any values that result in any inputs, any domain values that would result in division by 0. And so we just have to take the denominator and set it equal to 0 and solve to see if there are any such values. So in this case, whether we solve via square roots, or if we were to factor this into x plus 3 times x minus 3, and then solve that way, there are two values that are going to be excluded, 3 and negative 3. So the way that we can describe the domain then is we say it's all real numbers, and then we throw in a comma there, except x cannot equal, and then we can list off the numbers that are thrown out of the domain. So in this case that would be plus or minus 3. So we need to start with that all real number statement to indicate that it's everything, and then we've got our exception that x cannot equal 3 or negative 3. Second category is square root functions. In the case of the square root functions, to be in the domain of all real numbers, we can't have any imaginary results. So in this case, I'm going to take whatever is underneath the square root symbol, and I'm going to set it greater than or equal to 0. And so then I'm just going to solve that inequality. Now, if it's a linear inequality, we could just solve under our usual circumstances. In this case, with a polynomial inequality, I'm going to have to go through and think about my key points and then determine where the graph has solutions or does not. Now, for this one here, we can kind of think it through. As long as x is between negative 5 and 5, we're going to be fine. If we're anything bigger than that, then we're going to be 25 minus, let's say if we plugged in 6 or negative 6, we'd have 25 minus 36, which would give us a negative underneath the square root symbol, which if we're talking about real numbers, would not work for us. So in this case, for our domain, we could just say negative 5 is less than or equal to x, which is less than or equal to 5. So x has to be between those values. So again, in this case, we could kind of think this one through a little bit to see what our domain is. If it's anything more complicated, then we'd have to go through our polynomial inequality solving process from the previous chapter. And then the last category of types of functions that have domains other than our default of all real numbers are logarithmic functions. We're not going to spend a lot of time on this here because we have an entire unit that's devoted to logarithmic functions. But in this case here, logarithmic functions will point out that you cannot take the log of a non-positive number, meaning you can't take the log of a negative, can't take the log of 0. If you don't know what a log is, again, you don't need to worry about that. I just want to point this out as a little foreshadowing for the future. So right here, similar to what we did with the square root functions, I'm going to take the inside there, but I'm not going to make it greater than or equal to 0. It's going to be greater than 0. I can't take the log of 0 either. And so if I just solve that inequality, we get x is greater than 5, and so that's going to be our domain in this case. So if there's just a couple of numbers that are going to be excluded, then we use this all real numbers, comma, and then list off the excluded values. If it's a more restrictive type of setup like what we see here with the boundaries of negative 5 and 5, or even an unbounded inequality like we see here, we don't need to have it be list off the all real numbers component to it. It's implied in those statements that it's everything, x is everything greater than 5, or x is everything between negative 5 and 5. So, little conversation about domain here. Again, the default is all real numbers, but there are these three exceptions that we have to consider. And so if we're dealing with a function, a rational function, a square root function, or later a logarithm, these are the exceptions that we have to consider.